Today I just want to take all the things which we have learned in this course, so it's like end of this course, and calculate electronic properties of some material, zirconium, sulfur, and here is algorithm which I propose. So I propose to take all this. maybe we will not have enough time for this, but this will be then your homework. And maybe we will have problems with phonon spectrum, because I calculated it before our seminar, and with our normal accuracy, it was not normal. So it was not enough. It was not enough accuracy for phonons, and then I had time to recalculate it. So today we will do it with higher accuracy, and we will see what we will get. And also we will calculate band structure, those, combine them with together to see what atoms give what bands. And we also will compute Fermi surface, and we will need our virtual machines for this. I hope you didn't delete our virtual machines, because we have XCrisDen there. So XCrisDen in cluster has no, so there is no, it's not, okay, our cluster don't have this visual things. That's why we can't install the XCrisDen. So let's start. Let's start with maybe some information about zirconium sulfur. It's like it's a structure with the salt. No, zirconium S is a structure with salt-like crystal symmetry. Yeah, you see such things, and we have just like sulfur, like zirconium, sulfur, zirconium, and then they will go one to one. Yes, it's cubic symmetry. There in primitive cell we have two. In conventional cell we have 8 atoms, but as this is a cubic crystal structure, we can reduce it to primitive cell, and we can use only 2 atoms. And we will make these calculations, and we will I hope we will get something like this at the end of our calculations. And also this material tend to be a superconductor, but with rather small small critical temperature. So here is some paper of guys and guys who wrote this paper. You see, it's 2012, 2020. So it's like 4 years ago, and they just took these two materials and made the same batch of calculations, which we will do. So they calculated phonon density of states, they calculated this Eli-Ashburn spectral functions, they calculated superconductive transition temperature, and I think maybe each of us can do the same. So we can write such kind of paper with the knowledge we have now. Okay, so let's go to our calculations. I have it in lab 19. You also have, and we have a lot of folders. Yeah, if you remember, we started only with SCF folder. It was our laboratory work 1. Now it's laboratory work 19, and we have 6 different folders and a lot of properties which we can calculate. So let's go to relaxation folder. Let's discuss briefly, just for history, this file. So we have here a control panel. The main thing here is calculation type. We see relax. It means that we can provide relaxation and the relaxation will change the unit cell and will change positions of atoms. Then system IBRAF2 is IBRAF2 is cubic FCC lattice. So this is our lattice. If I want to take a crystal structure with 8 atoms, I should use IBRAF1. And then I will have this only three values. But if I want to take 2 atoms, I had to take this conventional cell. Okay. Also, I took ultra soft pseudo potentials, US. So before we used projected augmented wave pseudo potentials, now we use ultra soft because this routine for superconducting properties it was made only for ultra soft pseudo potentials. But for ultra soft pseudo potentials, we should increase energy cutoff for density, for electronic density. And and our 2 atoms, zirconium and sulfur, 0, 0, 0, 0, 5, 0, 5, 0, 5. And copoints 888. It should be enough for calculation. So let's start the calculation. But it starts from the really bad structure. You will see that we can see how it changed. So it was 992 Bohr, and now it's like 966, 76. So I should copy this LDM. Yeah, Igor also finished. So I should copy this LDM and move to. So I want to include it into my SCF file. The LDM changed parameters. Oh, let's try maybe to increase also here. You cut WFC. I mean, we can increase it to 800 maybe. We need these files from SCF calculation for band structures, for DOS, and for phonon spectra. For phonon spectra, we had to have them very precise. So that's why we have a lot of key points. That's why we have convergence threshold -12, which is huge. Increased YCAT WFC. Let's try. Let's try these parameters. And also we have another folder with SCF A to F. It's for LHberg function. I also have to change CLDM here. The only difference, so don't forget to change the cut WFC, and the only difference this function L2F, which allows us to calculate data needed to plot LHberg spectral function, and here is increased key points 24, 24, 24. We also for this LHberg sync we need a lot of points. We need good mesh. That's why it is 24. Okay, I will go to electron-phonon folder. Now we will start it, and then we will go to bands and DOS. And when it will be calculated, I think we can plot our bands and DOS. I also want to slightly change this file elf-in. Maybe I have done it. I took threshold inside our representations minus 14. Last time it was minus 12, and I also took minus 12 when I do these calculations at home, but it was not enough accuracy. That's why probably this is the thing, this accuracy. And also I took Q mesh, it just to save some time. I hope this will work. So what we should do next? We should copy the file. Yeah, we should copy the file from SCF file, SCF save file. And then from SCF A to F, I should take this file. Yeah, I hope it was finished. I think it works. We have only 3 Q points. I hope it will work. Okay, so let's, if you have started the calculation, let's forget about it for some time. It will take like maybe 30 minutes. And let's move to Ben's and DOS calculations. I propose to start with Ben's calculations. So now we are here. We have not done these calculations for quite a while because we was focused on phonons, and now it's time to revive our knowledge. So Ben's structure calculations. Ben's in with pw.x module, and then Ben's module Ben's.x for post-processing. What's the... I will revive your knowledge about this file, Ben's in. So here, also I had also changed CellDM1. CellDM1, and then I had to increase YKWFC. And yeah, here, the main differences. Ben's calculation time, it's obviously, and this pass. I took the pass from we can do it from sig pass. I will take some file, for example, this file. I will open it at sig pass. Yeah, this crazy brilliant zone for typical for cubic structure, and our structure, here it is, zirconium S, and here we have the path, but this path differs from this path, so I choose this because I want to. I want to compare it with this file. This file, I took this file, gamma x omega k, and I took labels from here, gamma x omega k, and so on. So the path from this file, not from sig path. I think they are the same. They just took this at first, then they combined it in some way, and whatever. Yeah, I want to compare it with it. That's why I took this 10 points. And let's start the calculation. I hope you remember all those things.
I think you should change Q.
Yeah, I forgot
the
about
script.
it.
Yeah.
It crashed.
It's PWX and Ben's files.
You mean script is incorrect because here is Benz. You see Benz X. Yeah, you're right. PW and Benz. And I also had to copy files from NSCF folder, from this folder. Yeah, now
Do you also copy the file from A to F folder?
No. You see, this A to F, we need it only to calculate Eliashberg function. Eliashberg function we calculate from electron-phonon interactions. That's why we need it only in the folder of ELF here, because we calculate electron-phonon interactions here. But here it just bends, so we just need this pre-calculated electronic density stored in this folder and XML file from common SCF folder. That's all. Now it should work. Yeah, now about this file, bends2 in. Yeah, it's just a file for post-processing, nothing special. It will create this file, fill bend, zirconium S bends that, and then we will plot it. So I had to change script again. It was firstly it was with bends.x, so we had to return it, and bends2. Here it will be bends2. Yeah. So yeah, it will take a few seconds. Yeah, it finished. 1 minute. I was wrong. And now, if it was finished for you, I propose to go to interactive model. It assigns us on the node. For me, it's 46. By the way, if you have a different node from 46, you can write it in chat. It's interesting if it assigns us for different nodes. Of 19 bends. And here I have this file, just Python script. You saw it a lot of times, just to remind you it. So it Igor has also 46 node. So we're on the same node. What things you had to write here? Fermi energy, then interval in which we will create this plot. I choose -5 to 5. Here it's from -5 to 10, but okay. And then high symmetry points. So each of these points, if we will take this 3D structure, brilliant zone, and this path, and then if we will just calculate the distances between these points and add 1 to 1, we will have this these distances. So some distance from here to here, from here, and so on. And this data, it shows us the coordinates of these points of x and so on. Gamma point has coordinate 0. It's not here. Then number of lines which goes from each high symmetry point, and here our ticks. So like names of these points. at coordinates and at these coordinates. Then it will save it in zirconium S file. So I just do this command Python 6. You should create the file. What things we can see? We can see gamma. So at gamma near 3.5 maybe, you have this bands and a lot of bands here. 1, 2, 3, 4, 5 bands. So what's here? This gamma point, these 3 bands, here are they. Here we have these 5 bands. This white band goes to X. Yeah, and here, so it's the same. So we have correctly plotted this band structure. Now let's proceed to those calculations. Density of states. It's second branch of our calculations. So we have finished successfully this. Now we are going to those, and we should make non-self-consistent calculations at first. Yeah, here is NSCF, non-self-consistent file. What's the difference from self-consistent? So here we have only one cycle. In self-consistent, we have a lot of cycles till it converges. Here we have only one cycle, and we use pre-calculated electronic density, which we done in SCF step. I should increase maybe here. Our cutoffs, and NBND should be 12. Should be 20. And the difference is tetrahedral opt. So it's the best occupations rule to calculate density of states. And we had also increased key points. It was 12, now it's 18. And it should be enough. The Zoom works annoyingly. Okay. Then I just started. Let's check is everything okay. Not okay. You see here executable FS Fermi surface. You have to change it to PW. And here should be NSCF. So we have to copy save folder and XML folder here. Now it will work. When I made my calculations for phonons, it was like minus 0.5 terahertz. You see the problem. Negative modus at 0 point at the gamma point. Not huge negative modus is okay. So probably minus 11 will be okay. Minus 0.3 terahertz. But minus 0.5 terahertz was not okay. Maybe this will be better. But we increased the accuracy, and we got here not so huge. Well, maybe I can show you to compare it from my test calculations. Minus 59 and minus 34. So I increased accuracy in SCF. So I increased the number of key points. Then I increased threshold from -12 to -14 in ELF, and I got and it reduced twicely this negative modus. So probably this will be okay, but maybe not. With this modus, I got something crazy. So it's not good thing. Now I'm going to post-processing. What's our next step? Our next step is to calculate partial dose for the structure. We do it with proj.wfc module and with file pdos in. This is very simple file. So as pdos in. You see, it just prefix outdir file which contains output, and delta E I once or maybe twice or maybe three times explain what is it. So it's the step in this in energy. It's energy step. So 0.01. It creates the number of states within this small delta E. I should change PS script. Executable proj.wfc. And here should be pdos. That's all changes. Okay, let's start the calculation. It will take a while. Now we have a lot of these files with projections on each orbital. So we have projections on zirconium s orbitals, p orbitals, on d orbitals, and on sulfur s and p orbitals. I want to collect them and to make projections on zirconium and on sulfur. For this, I had to use this some pdos routine. I know you don't like it. I also don't like it because it's like regular expressions. This some pdos. I made a small script just to easy this calculation. So it's very simple. It's like export this library and then some pdos with direct path to some pdos module. So, and we will create, we will combine zirconium and S into zirconium S total dose. We will have the dose just for zirconium, just for S. If you want, we can include also S, P, and them. Or maybe if you will have time to do it. So I had to go to the node. Return to my folder. And just start the script some pdos with this with dot and slash some. Before I should do the each mod plus x some pdos dot x. So it means dot sh. It means that I will make this file executable. Maybe you remember such command from Yizhe seminars. Dot slash some pdos. Yeah, you see, it worked. So it just export that library and then executed the commands, all the three commands. And we took these files, all the files, combined them in one And then we took only files for zirconium, combined in file for zirconium, and the same for sulfur. Now we shouldn't go out from the node because we can plot it. VE, VI, CRS, PDOS, PI. We already have this file to plot it. Here, those file pass 1, 2, 3 to our files with those total zirconium S, Fermi energy, and some just data, just size of the plot. I used only also -5 and 5, the same for as for band structure, because we had to plot them 1 to 1. That's why I want them to have the same size. It's very simple. I think it's a rather simple script. Python 6 RS PDOS pi. I hope it worked. So what do we see? We see a lot of states at Fermi level. That means that it's a good conductor. Then we see that almost all conductivity is zirconium, and I think that is d electrons of zirconium. So we can check it, of course, but I think that d electrons of zirconium are responsible for it, because if you will look at its stellar potential, you will see that it has this 4D states at outer. So we have outer D states with 2 electrons, but D states we each can they can take 10 electrons together. So it has 8 places where other electrons can go. So that's it creates huge conductivity. Yeah, and S, I think it's p orbitals of S sulfur. So they combine and make all the states. And if we will check here, you see that it's the same. At 2 we have those peaks. At 2 yeah, they are the same. So I think they are the same. But now we had to create such a plot. To make such plot, we can copy a file. I had to copy a file with bands from my folder. It should be this zirconium S bands.gnu. And we have script RS bands PDOS together. So it's just like Frankenstein, just combination of 2 scripts. It's some first part is some bands structure. You see this key points coordinates, and then we have DOS, but it's not like this horizontal DOS, it's vertical DOS. I just reversed the axis, and it should create the file named zirconium S DOS bands plot.
And what did you copy again?
I copied this file, zirconium bands.gnu from bands folder. Bands.gnu, it's just file with all data to calculate to plot band structure, and script should open it. So in script I have command just to open it here, band file pass. Probably it's better if I will write here like ./bands. So it means that I had to make some pass to the folder with this file and not copy. So maybe it's better, but now it's not like this. band C.6 and zirconium S, band speed was pi. Yeah, now we can check. Now we can compare with this file with this spot, and I think that they are the same. If we do this comparison, so they are the same. We have the same dose. We have the same bands. We have the same dose, and we see here dominates sulfur at lower energy. Yeah, so sulfur makes this valence bands, and then it's zirconium starts to dominate. So all these bands mostly created by zirconium. We finished this and this thing. Now we had to go to calculate Fermi surface. It's very easy, super easy, but we had to launch a virtual machine. It may be tricky. So we have this file, zirconium S Fermi in. It is super simple prefix and audio, but Fermi should be here. Then I should change QE script. I should change it to make FS. Here should be module FS means Fermi surface, and here should be Fermi and Fermi. I should exit the node and start the calculation. Yeah, I'm still on the node. And start calculation. Sub Q, yeah. Yes, this file in the end. Zirconium S, CRS, FS, BXSF. This file. I can open it. Here it is. I open terminal. And in terminal, I should type this command. So I should launch xcrease_den. This command xcrease_den minus bxsf and name of the file. We have 5 bands. You proceed with the step. What's your progress now?
What's the command again?
This command. Wow. xcrease_den minus bxsf and name of file. So it's like just your launch xcrease_den, then you comment then you make the same comment as extension of the file. Just to open it. So let's look for the bands hunters. I think that this band, you see, this band goes down to 11.6 electron volts, and so ever. So it's like 4.2 electron volts below the Fermi level, and we have this band. we have only one band here, which goes, or maybe probably this also goes down, but I think that this is this band structure. So we have this band, here it is, and then it goes up. It's first band, yeah, it's band first, and it crosses Fermi level very slightly in this point. You see, very interesting point, yeah? Like two bands, they're touching at Fermi level. Crossed here, then it cross it again, second time, 2 times, then it crosses it for third time, 3 times, 5 times, 6 times. So it's like at least 6 times it crosses Fermi level. It's band 1, and we have this crazy band. This is band 1. See, how much times it crossed Fermi level? 6. Yes, 1, 2, 3, 4, 5, 6. Here it is. Then we have second band. Second band, yeah, I think it is the most interesting band, and then we are going to the second band. It will be harder to check where is it. It should be one of these bands. So we have 2 bands. You see, we have 2 bands which goes from the same point. I think that they are bands 2 and 3 because they also have the same point. 2 and 3. I don't know. Band 3 slightly wider, band 2 slightly lesser. So we have, I think that this is band 3 because it goes, you see, it goes up. This is band 3. It goes somewhere here. Then it crosses Fermi level here and goes somewhere. Yeah, so it's band 3. And band 2, probably this band. So it goes, it also crosses Fermi level here. And then, yeah, then it goes somewhere here, then it touches our band 1. We have this crazy band here in the center. Why in the center? Because it starts from gamma point. And if I will combine them, what I will see? I don't see that they are touching, like touch. But almost, so they almost touching in few places, like maybe these places, or maybe this, yeah. Somewhere it should be a place where this band touches with this band, but I can find it. And also we have, you see, band 3, band 4, and band 5. They're all inside. Yeah, it's like band 5, the smallest here. It means band 5. It means that it's goes from somewhere. I think that band 5 is this band. You see, it goes from somewhere, and then it crosses Fermi level in this gamma point, and it is not so wide at these points as in other bands. So like this is the smallest, this is band 5. Then we have this band, probably it's band 4. And we have another bands, like maybe band 3 or 2 and band 1. Yeah. You see, like 1, 2, 3, 4, 5 it's like dome. It's like one band, then a bigger band which contains this band, then even bigger bands which contain these two bands, and we can see it all here. So we have the smallest band, then bigger band, then bigger band, then band which contains all the three bands, and then we see this crazy band which in some way contains all the bands, and we have such beautiful Fermi structure. I think it's really nice. We'll make.
Sometimes it's difficult to wrap your head around because it's all in 3D. And it's
it's 3D. We should imagine it.
Because if we took energy also, it would be a 4D surface, and we see it's. I mean, when we're talking about surface, in like regular world, we are thinking usually of 2D stuff.
Yeah, of course.
Here, everything we see is kind of a 3D surface of a 4D object, if you can say that.
Yeah, but
energy.
Originally it's 3D object. Yeah, but then we plot such 2D plots and say, and we think in these terms. We think in these terms. Yeah, that's why it is useful maybe to see the wideness of the band width, because you see that these bands go like minus, like almost 4 electron volts, like here. Yeah, and you see that we have only one band which goes here, and this band is interesting because it crosses Fermi level.
The number of crossings for band 1 included in our 2D plot. Does it correspond to the number of yellow faces on this?
I think yes. Yeah, I think yes. So of course you had to take it into account that there should be some symmetry. So I think that symmetry, like maybe 2 or 3 times multiplicates all those images. I can't estimate.
So you mean that the 2D picture gives us degenerate?
I mean that 2D picture gives us only this, and all these planes, they are created by symmetry, all other places. But we can see in 2D plot this thing. Yeah, you see 1, 2, 3, 4, 5, 6 points where it crosses. Yeah, it's like, yeah, it's rather crazy. I think that this 6 arrows, they means for number of times which it crosses Fermi level. So it's like, I don't sure that it crosses here, maybe not, but it's like 1, 2, and 3, 4, 5, and 6. Yeah, 6 times.
By the way, my ELF calculation has finished.
I think that my also finished. So if you have some questions about it, because I want to close Fermi, I will make some screenshot, and I want to close it because my computer don't like it. Your ELF was finished. Let's try to make some post-processing. Yeah, okay. So we have finished successfully 1, 2, 3 branches. We have only one branch. I don't sure that if we will finish successfully, but we can try. Because you remember that negative modus. So next step, post-processing, Q to R. CRS, Q to R. Post-processing, it takes these dynamical matrices then from these dynamical matrices, it calculates interatomic forces and stores them at this file FC. Yeah. I made this small script also post-processing, ELF post-processing. So here you should change it for Q to R. Q to R. Yeah. Q to R, and then launch. But you should notice that you should launch ELF-PP, not QE, because maybe because I just wanted to type QE. Looks like it works. You see, you have 3 Q points. First stands just for 1, second for 4, and third for 3. Together 8. Okay, we done it. Next step, matdyn file crs matdyn.in. It will take as input this interatomic force constants, and from then create this frequency file in real space. And here is our path, which is the same, which is the path for band structure. So I want to change LFPP. This is the moment where everything can go not in the direction I want. Because that negative frequencies can be left in real space. And they can't exist in real space. That's why that's the error. Qsub LFPP. More or less, it is better than the plot which I had. But the problem, you see, it goes somewhere to the minuses.
Yeah, but not so much, let's say.
I can increase. It was like -5. Let's
Okay, it's just a little.
I mean minus 30. Okay, just to check. Yeah, you see, it goes to the negative path. So it means that our parameters wasn't enough accurate. But maybe it's also a good thing from an educational point of view. So if you take not accurate parameters, you can got this negative frequencies. Negative frequencies, it means we have discussed it when we done con anomalies. So negative frequencies means that our structure is dynamically unstable. So it wants to change atoms in some way to become dynamically stable. But zirconium S, I think everything should be okay with zirconium S. But maybe, you see, maybe this zirconium S which I took, no, it's like, you see, energy above who? Yeah, what does it mean? It means stability phase diagram. So if we have 0 energy above who, it means that the structure is stable. If we have some energy above who, it means that its energy more than energy of stable structure. It means that it's metastable. And the structure which I took zirconium S cubic. It was experimentally confirmed, so everything should be okay. 2 atoms. I took it because it was 2 atoms, not because it's super stable. But you see, 0.09 electron volts above convex Hall. So probably it's metastable. Probably we done everything correct, but probably our structure is not good. So if it's only 0.09 electron volts, it means that it can try to go to rearrange atoms into stable form.
I think it doesn't necessarily mean that the structure isn't stable if its energy is slightly above the hull. It just means that in the space of all possible configuration of zirconium S, it is not the most energetically stable.
Yes. Yeah, I agree. But you see, we have zirconium S, which is stable. This zirconium S file. It has 4 atoms. Yeah, 2 and 2, 4 atoms. It's tetragonal, not like cubic. This is stable structure. So maybe this plot indicates us that we deal with really not so good structure, zirconium S. Because when I made it by myself, I will show you what I got by myself. It was really crazy. It was, this plot is good plot, but what I got, it was like, something you don't want to see. This is absolutely terrible plot. I expanded its range, so it was firstly here. So this was our range, and it was really crazy. And here, this means that we have really not enough accuracy. This thing, but probably the plot that we got, maybe it's not our problems. So maybe we made everything correctly, but maybe the structure is not okay. Now we do the same calculations as I done by myself, but with higher accuracy. I increased threshold in phonon calculations from -12 to -14. Then I increased YCAT WFC from 70 to 80. And I increased the number of components from 8 to 12. And you see that the difference was really huge.
Yeah. Maybe you should also increase the Q point mesh.
Maybe if you can increase Q points, maybe if you maybe we should make better calculations, because you see we made our relaxations with 888 point mesh, but but for SF we moved to 12. When we do this, some stress should appear on our cell.
And as I told, for me, for example, the stress wasn't completely relaxed. It was 001.
Maybe that's not a super huge problem, but maybe is. But maybe we made everything okay. Yeah, and the structure is not good. Sometimes structure is not good. If we is sometimes when we see such plot, structure is not good. So let's proceed. Let's so it's like 15 now. We don't have enough time. Let's go. We have two. We have this. It's zirconium. Yes. There are two steps left. We can do them very quickly and check if we can obtain a correct temperature, because from that, because I couldn't obtain it by myself, because the plot was really terrible. That's a really terrible plot. Okay, exit from the node. Now my file is matdyn A2F in. It's file to calculate. So here is mistake. Please change it. 333 on 222. It was mistake. So is file to calculate phonon dose and algebra function. Please don't forget to change it. To change 333 on 222. Then I should change my script. I had to add just this A2F here and A2F here. That's all. Let's start. Started. No, not L, but Q sub elf PP. Probably we can try to plot this algebra function, but I suggest that we can go directly to lambda. Just do it as some intermediate step. Because from minute to minute, they will take our zoom. So it's like matdyn to F out. Yeah, should be okay. And now lambda. We have to make some changes in lambda file. I will show you this, what we had to do. This lambda file. But this lambda file was I made for my calculations, which was different in some ways. For example, I had more number of Q points. What can we do? We can we should open also Q2R out. And here I see all the things. Q1 like 0, 0, 0. So here should be number of Q points. Here should be Q point 1. It's 0, 0, 0, and its weight. It means how many Q points it contains by its symmetry. So how many I don't know, not irreducible representations, not irreducible. Okay, this Q point takes 4, and next Q point takes 3. One moment, I will check is everything okay with the Q points. Should be sure that yeah, 0 minus 5, 0, 5, 0, 5 minus 0, 5, 0, 5, this, and here should be this key point. And it contains 3 key points by symmetry. Yeah, and we should delete this. And also we should delete this because we have only 3 key points. That's the differences. Let's check if it works. Now let's try. It's very interesting for me what we will have, what we will get. We should change in our LFP lambda. 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 Yeah, you see, we didn't get we get nothing. We got the lambda, but maybe that maybe our accuracy was really not good enough to calculate omega and c. Maybe it don't works with that with that negative frequencies. So at this point we failed. I think that maybe that parameters was not enough, was not good enough. I mean the parameters from SCF. I mean maybe we had to make more number of copoints. Maybe it should be not minus 12, but maybe minus 14, or maybe minus 16 even. Then maybe this accuracy was not was also not enough. Like minus 14 should be like minus 16, and maybe we had to make relaxations, but not with like 8, 8, 8 copoints, but with like maybe 16, 16, 16 copoints, and then we should make a SCF calculation with the same number of copoints. In this way, we for sure will not have any stress on the cell, and the stress will not change our results. Nevertheless, I think it was rather educatable also, because before we worked with phonons which I pre-calculated, and it was everything okay with these phonons. And now we see the more or less real situation, because our parameters was not accurate enough to get normal phonons. And maybe our material is not good. These guys from they worked not with zirconium S, with our zirconium S, but with this zirconium S, with stable zirconium S. So probably if we work with this material, but it has 4 atoms, it's rather no, it will take rather huge amount of time, rather long.